So we get to start talking about atoms in chapter 2 and 3. Chapters 2 and 3 are really similar. We're just going to start out with the most elementary aspects of atoms. So let's start off with simply defining what an atom is. Does anybody have an idea of what they think an atom is? Just in generic terms? If you had to explain it to a sibling or a parent who's never taken chemistry, what do you think?
A single particle of matter.
Yeah, so it's kind of like the most elemental single particles that we can have, right? So I like to call these the building blocks of matter. All right, and then for a long time there was this idea that atoms are unique because you can't cut them into smaller pieces, right? However, more recently, at least in the grand scheme of things, we've learned that that's not quite the case. Does anybody know an example of situations where we can cut an atom? What? Yeah, an atom bomb, right? So here's a picture of an atom bomb. If you are interested in history at all, I highly recommend reading about the Bikini Atoll tests. Essentially what happened was in the 1950s, there was this race between the Soviet Union and the Americans to develop the most powerful weapons. The reason for that was our missile guidance systems were quite crummy. So it's like, even if you miss by a few miles, yeah, you'll be fine, right? It's going to take out a 10-mile radius chunk of land. The problem was, in the initial tests with the hydrogen bombs in particular, they underestimated the yields of the weapons, and they ended up contaminating a huge amount of ocean water and land, and displaced a huge number of native inhabitants. It's one of this, in my opinion, one of the big black marks on American history of things we shouldn't have done. So it's an interesting read. If you want to read about it, I'll try to post it on the class website as the topic of the week. All right, so it's pretty interesting. And if you look at atoms for a long time, they were more theoretical, right? We couldn't visualize them until very recently. So I wanted to show you this video, and I'll try to get the sound going too. IBM was actually able to visualize individual atoms using special microscopes. And they were actually able to move individual atoms around to make a mini movie. And so they made this movie called A Boy and His Ball, I believe, or A Boy and His Atom. It's kind of cheesy, but I find it fascinating that we can visualize atoms, move them around, and make a movie now. The coolest thing, in my opinion, is atomic theory has been around since the early 1800s, where we theorized the idea of an atom. But we had no direct evidence that atoms existed until really recently, where we were able to visualize them. More recently, you can actually see individual bonds between atoms. You can see actual bonds being made and broken. It is incredible. A lot of people think that science is kind of slowing down and that we've discovered everything there is to know about chemistry. That is not the case at all. There's a lot left out there to be investigated.
How do they do that? How are they moving that?
They use special electron microscopes. And with electron microscopes, you can actually basically pick up an atom and move it around a little bit. It's really interesting stuff, though. All right, so I like showing some of those unique videos, but let's dive into the idea of atomic theory and how they got there. And in order to do this, we need to talk about some basic scientific laws. All right, and I want to review a little bit of terminology. The difference between a theory and a law. So what's the difference between a theory and a law? Who remembers? One has a math equation. Which one? A law, right? So a law is a summary, not an explanation. And like I said before, it often has a formula. Whereas a theory isn't a summary, it's an explanation, right? That is supported by data. A law, on the other hand, doesn't explain why something occurs, it's just a summary. Make sense? People oftentimes misuse those. So let's take a look at the first and most basic law in chemistry, and this is the conservation of mass. And like I said before, this is a summary, so it's a law. It doesn't explain why conservation of mass occurs, it just says it occurs, right? And so let's take a look at a really simple example. In this example, we've got 100 grams of mercuric oxide. And if you heat this up and react it, you can actually create 92.61 grams of mercury and 7.39 grams of oxygen. As you saw in lab yesterday, some reactions produce a gas, but that gas still has mass, which is why we put the balloon on the test tube, so that that gas couldn't escape. We could actually measure the mass of a gas. The big takeaway from this is that both of these, if you add them together, equals 100 grams. So you put 100 grams in, you get 100 grams out, right? So yesterday, ideally, with that test tube reaction, you had exactly the same mass going in and out. Sometimes there's a little bit of margin of error depending on your scale, or if anything else happened like a balloon leakage. So that's the idea of conservation of mass. You can't create or destroy mass. Pretty simple concept, but at the time it was pretty revolutionary. A lot of people, especially with reactions that produce gas, thought that they were actually losing matter in a reaction. It wasn't until the 1700s that people were saying, wait, gas actually has mass too. All right, so let's take a look at this using a new example. It's a common one for a lot of heating systems, where you take CH4, this is methane, it's found in natural gas. And in your house, you have natural gas maybe piped in, and it reacts with oxygen, typically pulled in from the outside. And when you burn this, you make what? Does anybody know what one of the products of combustion is? Not close, not CH2, CO2, right? Carbon dioxide. So when you burn things, you produce carbon dioxide, assuming it's complete combustion. And you also produce water vapor. That's why oftentimes natural gas is referred to as a clean fuel. Unlike coal, which produces a lot of soot, natural gas produces water and carbon dioxide. One of the other public service announcements I wanted to make is incomplete combustion results in another gas that's pretty similar to CO2. What's that gas? You might have a detector in your house. Carbon monoxide, right? So CO is produced if you have incomplete combustion. The difference between those is subtle, right? Just one oxygen atom, but it's an important difference. If you are being poisoned by CO2, it's similar to holding your breath, right? You get that buildup of lactic acid and you feel like you're suffocating. With CO, carbon monoxide, you don't feel that. Instead, you get sleepy, want to take a nap, and then die. That's why it's important to have a CO detector in your house. Very, very important PSA announcement. Check your batteries too. Some family just died in Mexico from a leak in the condo that they were staying in. All right, but that's my soapbox. I'm going to get off that now. If we look at this, we've got some problems though. One of the problems that I see is that we have two oxygen atoms over here, and then we've got 3 oxygen atoms on the right-hand side. And so what chemists often have to do is something called bouncing a chemical equation, and we're going to practice this later, but this is a preview. And in order to bounce this, what we do is we put in numbers, and we say you actually need 2 oxygen molecules and 1 methane molecule. So the 1 and the 2 basically represent the number of molecules. Or the ratio needed in this reaction. And then if we go to the right-hand side, we can also say there's a 2-to-1 ratio, so we put in these reaction coefficients. This is a preview of what we'll be doing a lot of later, but we're going to practice bouncing these. The goal is to have the same number of atoms going in as coming out, right? Because we can't create or destroy atoms. We're just moving them around from one molecule to another. All right? And the idea with this is the total mass going in is equal to the total mass coming out. Alternatively, like I said, another way of viewing this is number of atoms in equals number of atoms out. But it's very important that we bounce reactions so that we're not gaining or losing atoms. And so we'll practice that a lot more later. Does that make sense? All right. There's another law that's also important, and it seems somewhat intuitive, but it was very revolutionary in the 1800s. And this is the law of defined proportions. All right, and with the law of defined proportions, it's basically saying that a compound or a molecule has a fixed ratio of atoms. Contains the same elements in the same ratio. Whoop. And I'll show you an example, a simple one that we're all familiar with. This is water. What's the molecular formula for water? H2O, right? One we hear a lot about. And basically what this means is that there is always a 2-to-1 ratio of hydrogen to oxygen. It's never going to be 4-to-1. It's never going to be 3-to-1. Water, by its very definition, is always going to be a 2-to-1 ratio. And there's some unique examples of this. So, for example, in this first picture, we've got 10 grams of lead reacting with 1.55 grams of sulfur to make 11.55 grams of lead. If you notice, the mass going in is the same as the mass coming out. Makes sense? That's the law of conservation of mass. In the next one, though, what they're doing is that they're adding in 1.45 grams of sulfur. And as a result of that, we're not going to make any more lead, or lead sulfide, excuse me, because we've already met that perfect ratio in the first reaction. So if we add in more sulfur, we end up with leftover sulfur. So that perfect ratio is already predefined in reaction 1. If we add in any extra reagent, we're just getting leftovers, right? Same thing over here where they add in 8 grams of lead. If you do this, you just end up with leftover lead. So the first one is a perfect ratio. These ones have leftovers. Does that make sense? I know it seems pretty elementary, but it's good to review this. All right, let's take a look at a few more examples. I like a lot of the more relevant examples to our day-to-day life. Lead sulfide's not super relevant. One of the really interesting reactions right now is taking water and splitting water into hydrogen gas. And hydrogen gas is two hydrogen atoms bonded together, so we say H2. And then we say it's a gas by putting that G in between brackets. So you can split this into hydrogen gas and oxygen gas. And oxygen is similar, where it's two oxygen atoms bonded together, so we write O2. Then we say it's a gas by putting the G symbol behind it. All right, if we look at the atoms going in, we've got two hydrogens on the left, we've got two hydrogens on the right, so that's balanced. If we look over on the left-hand side, though, we've got one oxygen on the left and two on the right. So what we need to do is some math. And then we'd say, all right, we actually need two molecules of water. Now we've got four hydrogens on the left, four hydrogens on the right. That looks balanced to me. We've got two oxygens on the left, and we've got two oxygens on the right. So you can multiply all of the atoms to make sure that we're not gaining or losing mass. In order to accomplish this, you need a catalyst, and you need energy in order to split a water atom. It's not very happy being split. The reason why this is an interesting reaction is if we go up and we look at our previous reaction with methane. Like I said, methane's a common energy source for heating your house or a fuel for driving ships and trucks and things like that. But it's producing this gas, carbon dioxide. What's the downside to producing that gas? It's a greenhouse gas. So if you've read about climate change at all, we're pumping too much CO2 into our atmosphere. It's changing our overall planet and the way it's behaving. So there's a lot of talk of changes in weather, droughts, and an overall warming of our planet. So there is a lot of concern that we're producing too much CO2. So what they're trying to do is to figure out cheap ways of taking water, which is abundant on our planet, splitting it into hydrogen gas, and using this hydrogen as an energy source. So if you've ever heard about the new fuel cell vehicles being produced by Honda and Toyota and a bunch of other car manufacturers, they're actually trying to figure out ways to not only split water into hydrogen and oxygen, but to use that hydrogen gas as a fuel for automobiles. And that's a really exciting new branch of chemistry that's being explored. Typically to do this, they'll apply a cathode and anode to a water, so basically attach it to a battery with special metals, and that will bubble out oxygen and hydrogen. The reason why I like this example is let's take a look at this picture here. This is the hydrogen gas produced in this reaction, and this is the oxygen gas produced. And if we look at this, right, we're producing twice as much hydrogen gas as oxygen gas. And you can clearly see this in this picture, and it makes sense according to the law of defined proportions. So twice as much hydrogen gas is produced. The neat thing with this is when you burn hydrogen, what does it turn into? Think about it this way. It's the reverse reaction, right? When you burn hydrogen, it's reacting with oxygen in the air, and you form water. This is an ultra clean reaction. If you have water coming out of your tailpipe, that's one of the best case scenarios, right? So it's really interesting. The biggest problem with this is the catalyst. These catalysts required for this reaction are incredibly expensive and quite often are made of precious metals, things like platinum and palladium. And so what they're trying to do now is to develop cheap, abundant catalysts made of something like nickel that is an abundant element and is cheap to produce. The fuel cell cars now, I think, are in the like $70,000 range, and so they're trying to figure out ways of lowering the cost all around. All right, again, I'll get off my soapbox. Interesting stuff, though. I liked it.
Is that a safe vehicle to drive around with?
That's a good question. So another pitfall to this that a lot of people will argue about is, do you want to drive around with a gas tank full of an explosive gas?
I would.
No? But there are other people that say, what's the difference between having a car full of hydrogen gas and a car full of gasoline, right? They're both flammable fuel sources, and there's ways of making them safe. It's just more of an engineering challenge at that point, right? So trying to design safe cars is an interesting field.
I recommend next time somebody asks the difference between hydrogen and gasoline, you put up that first picture you had. Kaboom.
Yeah, exactly. Hydrogen is relatively safe to transport. It's just expensive to produce, and fuel cell vehicles are quite expensive right now. All right, let's go into atomic theory. This is going back to square one, where people were trying to take those two ideas of conservation of mass and defined proportions and try to describe some common explanations. All right, this was developed by John Dalton. In 1803, and it explains those two laws. So like I said, a theory is an explanation, a law is just a summary, often with a math formula, right? So let's look at the key parts of his theory. And for the most part, his theory holds up well today. So let's do the first. He said that all matter is composed of atoms. Whoops. Prior to this, there was a lot of mystical thought that maybe matter was made up of other things. So if you read philosophy books, the Greeks and Romans thought that it was made up of earth, wind, and fire, right? That's not necessarily true. That was more mystical. All matter is composed of atoms, and that was a big part of his theory. All right, number two is that all atoms of a given element are alike. And another way of thinking about this is they all react similarly with similar things, and we'll talk more about that later. So they're all similar as long as it's the same element, right? And there's a second part to this. And they are unique from other elements. It's pretty revolutionary at the time. One thing I will say is this theory has changed slightly. Not all atoms of a given element are alike. Let's take carbon, for example. Carbon is the stuff that makes up most biomolecules, right? It's an important atom in biology. However, carbon-14 is actually radioactive, right? Most carbon is not radioactive. Some of it is, though. He didn't understand the difference between those at the time. It wasn't well understood, and that's referred to as an isotope. We'll talk more about this later. Does anybody know what carbon-14 is used for? What do you think? Dating. So if you've ever taken a class where they say, this fossil is 60 million years old, the way they do that is actually measuring the amount of carbon-14 in that sample. It's an interesting process. And that's due to radioactive decay of carbon-14. All right, number 3 is that molecules are formed when atoms are combined in a fixed ratio. So that goes back to that water example. It's always a 2-to-1 ratio. It's never going to vary from that, right? And then number 4 is the last one. Number 4 says chemical reactions involve the rearrangement of reactions. And I'm going to add on to that, which can't be created or destroyed. And I will say, again, he didn't know about the atom bomb. That was pre-1800, or that was in the 1800s. They had no idea about splitting atoms. So he didn't know about nuclear chemistry. Another unique example, too, is with particle accelerators. How many of you have heard of those? So there's a few places on the planet where they actually will speed up atoms and slam them into other things, sometimes other atoms, sometimes other subatomic particles, and actually get them to break apart. So the last year or the year before, that Higgs boson particle was all over the news. Some people called it the God particle, although the guy who came up with it hates that term. And they can actually destroy atoms and study the inner components of atoms that way, but that's using very, very specialized chemistry. All right, so those are the 4 main components of his theory. Like I said, most of them hold up surprisingly well today. All right, there's another important thing that was discovered a little later by a Russian chemist, and this was the periodic table. Most of us are pretty familiar with the periodic table. We've got it right on the wall over there. And the chemist that worked with this was named Dmitry Mendeleev. Whoop, that should be a V. I forgot to put a picture up here, but if you can Google him. He looks like a wizard. It's kind of funny. All right, and his big project was organizing all of the elements. No, and we'll actually talk about that. And the interesting thing was, when he did this project, he only knew of 63 elements. How many elements are there today? If we look over there. If you look at the kind of bottom right-hand side, you see 116. It's somewhat debatable how many of those are legitimate. There's actually an international union that gets to pick which ones have enough data to support them, but there's approximately 116 elements today. That meant he was actually predicting new elements. And I'll show you how we did this. It was a pretty simple process. So for example, I'm going to zoom in on this a bit more. I'm going to look at lithium over here. He would react lithium with oxygen and make lithium oxide. And he noticed that whenever he did this, it was very, very reactive. It let off a lot of energy. And then he would go down to beryllium, and he realized it didn't really react as violently as with lithium. And then same thing with boron, same thing with carbon, same thing with nitrogen, same thing with oxygen, same thing with fluorine, same thing with neon. But then when he hit sodium, all of a sudden it reacted in the same way with oxygen. It let off a huge amount of energy. And then he would go through heavier and heavier elements, and he would again go all the way down to potassium and say, wow, these all react really similarly. And what he noticed was that the gap between these, in terms of the number of atoms, was about the same. And that's how he started organizing the periodic table. When you look at the periodic table today, all of the columns going up and down are atoms that have similar reactivities. So if you look at the far left-hand side, lithium, Li, is in the same column as sodium, which is Na, which is in the same column as potassium, which is K. And then we've got rubidium right below that. I don't believe he knew about that at the time, but actually predicted that there should be something in that spot. They just hadn't discovered it yet. Kind of interesting. All right, I'll show you a cool video, though. Oh, sorry.
Man, the chemistry can be, there's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, my present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under Argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
But imagine, if you will, letting off a hand grenade in a bathtub.
Right, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a very crucial seconds to get into our safety zone. Yes! Oh, that is more. Only on Brainiac do you get that kind of science. But I believe we can go one there. There is one more alkali metal we can really use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty to go off at any time.
That's it.
Oh, yes.
I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in the bathtub.
Right away, I'll leave it to that.
Thank you.
Okay, John, go for it. As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, franklin. But for some reason, they wouldn't let us have any of that. Except, there you go. Today's lesson.
Never mix alkali metals with water.
How did they get all these elements back then?
That's a good question. So the question was, how did they get those elements? They actually, today, have to use electrochemistry. If you open up a vial of, let's say, cesium, it will instantly react with the moisture in the air and explode. And so when they transport it immediately after they create it, they actually have to transport it in an oil solution. And if you know oil and water don't mix, that keeps the water nice and far away from it so it doesn't explode. But it's very hazardous to work with some of these. It's one reason why they won't let me do this demo in the classroom. So I did the next best thing, showed you the video. Yeah, pretty exciting though. It's also interesting if you notice too, quite often as you go down the periodic table on that side, they get more and more reactive. The same is also true for the second column, group 2A. If you go down that column, they also get quite explosive as well. We don't think of calcium as being explosive, but in some situations it can be. So we do have to be careful with a lot of those metals when they're pure metals. All right, so let's take a look at his table. You can see in his table, he had a lot of gaps in here, and that's what was so neat about it, was he predicted some undiscovered elements and was the first to organize all of the discovered elements at that time into a cohesive way and organize them based on their chemical reactivity. Today, the periodic table looks a lot more complicated, and our periodic table in our classroom doesn't have all the color coding in here, but if you notice, we describe different columns differently. I'm not going to get super into that, but some of the important ones are these ones that were just talked about in the video. These are referred to as the alkali metals. They're always on that far left-hand side. Another one that's pretty important over here, on the far right-hand side, these are the noble gases. And these are pretty unique too. Whereas alkali metals are very reactive, noble gases are actually the opposite. They're very unreactive. That's why they call them noble. They don't want to do anything. All right. There's also different elements in between. There's transition metals in this block. And these have varying degrees of reactivity. But exclusively metals in this block here. There are also some that don't really have very good homes. And if you notice, I like this one right here, Hg. Does anybody know what Hg stands for? I know that's hard to see in the back. It's mercury. Has anybody seen mercury? Mercury is a liquid metal. So it will actually flow like a liquid, but it has a metallic color. So it's kind of this oddball. There are a handful where they aren't solid metals, and those are kind of unique. All right, if you look at our periodic table, one easy way to spot the liquid metals is that they're highlighted in green. So mercury is a unique metal. Bromine is also a unique metal. There aren't many elements that are metals. Also on our periodic table, if you see the ones highlighted in red, those are all gases. So a lot of the elements are gases. The vast majority of them are solids though. So let's really quickly take a look at what the various sections in the periodic table mean. And I'll just make up pick an element. I won't make one up. And we'll do element number 26. So what's number 26 on the table? What's its symbol? Fe. Okay. And so on the periodic table, you see these numbers usually at the top. These are called the atomic number. This is important. And then down here, you've got the element symbol. And does anybody know the name for the element that has the symbol Fe? Iron. It's iron. It goes back to the Latin root, ferrous. So it's iron. That's the name in English. The interesting thing is the element symbols are universal. They're used across the globe. The element names might vary from language to language. All right, and then at the bottom, quite often what you see is a number with a decimal. And so, for example, with iron, let me keep it all the same. We've got 55.847. What this is the atomic mass, or average atomic mass. that means what's the average mass of one iron atom? And in this case, it's 55.847. It's not grams, right? We know one atom doesn't weigh 55 grams. Instead, what they do is they measure this in atomic mass units. And people will abbreviate atomic mass units as AMU. So it's a new unit for mass. All right, so let's try to define atomic mass. I'm just going to box this all in here. And like I said, AMU is atomic mass unit. And 1 AMU is equal to 1.6605 times 10 to the negative 24 grams. So you can actually use this as a unit conversion tool, right? So just like we practiced the other day, you can actually convert between AMU and grams if you want. Let's actually try doing that really quick. And I'm going to use Batman again. So how much does Batman weigh in AMU? And Batman is, let's assume, 95 kilograms. So I'll give you guys a minute to work on this, but see if you can actually convert the weight of a human being, in this case Batman, to the weight in AMU. Give you a hint too, we need to convert from kilograms to grams, right? Because AMU, the conversion that we have is in grams. So let's try to write that conversion down. 1 kilogram equals how many grams? 1,000. Okay, so that's another conversion we can use. Give me a thumbs up if you feel pretty confident in your answer. A few people. This is a good one to make sure you know how to type in everything correctly into your calculator. Like I said, it's always good to show your work. If you don't show your work and you get the problem wrong, you get no points. If you show your work, but maybe you type something in incorrectly in your calculator, you'll get most credit. So thumbs up if you think you got it now. All right, let's try doing this as a class. Like I said, start out with what you know. We know Batman is about 95 kilograms. And we want to cancel out kilograms. So should it go on the top or bottom? On the bottom, right? We want it to cancel out. And we have a kilogram to gram ratio. Does the 1,000 go on the top or the bottom now? On the top. It's partnered with the gram unit. 1 kilogram, so now we've canceled out the kilogram portion. We're left with grams. All right, now we want to cancel out grams, so we want that to be on bottom, and we've got a gram to AMU conversion. And we know that 1 AMU is 1.6605, I'm going to move this over, times 10 to the negative 24 grams. So now we're set to cancel out our grams, and we're left with units of AMU. All right, so when I type this into my calculator, I get 5.721168323. And this is multiplied by 10. I'm going to slide this over to the 28th AMU. All right. We're not quite done though. What's the last step? Sig figs. So we had how many sig figs originally? 2. That means we need 2 sig figs in our final answer. So let's change this. We need 2 sig figs, so it should be 5.7 times 10 to the 28th AMU. So this is another tool we have to convert from grams to AMU. Really quickly before we head out though, is one atom of carbon-12 is exactly 12 AMU. That's the universal standard that scientists have come up with to define AMU. And if we look at the periodic table, the elemental symbol for carbon is 12.01. Why is it showing us 12.01? Anybody know? Give you a hint, we talked about dating fossils. What element did they use to date fossils? Carbon-14, right? So not all carbon atoms are carbon-12. Carbon-14 actually weighs a little bit more than carbon-12. It's got 2 additional neutrons in it. And so when you see that 12.01 on the periodic table, what that means is it's the average of all carbon-12 atoms, the average of all carbon-13 atoms, and the average of all carbon-14 atoms combined. And most of the carbon around us is carbon-12. In fact, it's about 99%. Most is that, however, 1% is actually carbon-13, and there is a trace amount of carbon-14 because it's radioactive. The AMU listed on the periodic table is an average of all isotopes. So the key word here is average. Does that make sense? All right, believe it or not, we've already finished chapter 2. Chapter 2 is pretty quick. However, if you do have any questions or need any help with the pod, you're more than welcome to stop by my office before class tomorrow.